record. I don't know how good this recording is gonna be. Yep, I know. I'm pissed about it too. Today we are beginning, and this will be on the midterm, by the way. I'm making the first week fluffy. There's information here you will be tested on, but I'm not going to go, we're not going to go crazy on it. Oh, whether or not you feel that it's crazy hard depends on what you're bringing to the table. I'm trying to make this as straightforward as possible. Let me put it that way. I'm not going to try to break you. Okay, so this will be on the test. Focus, pay attention, and we'll continue it after. I claim that dynamics is the study of how things interact, how things exert forces on each other. Dynamics is the study of the causes of motion. We've been talking a lot about motion. We've been talking about how to mathematically describe how stuff moves, where it is, how fast it's going, which way it's going, how that is changing, all that. That's just describing what something is doing. Now we're going to talk about why is it doing it. This is a terrible phrase. I put this in quotes. You might have put an asterisk by it because we're going to see in a second that this is actually a common mistake is hidden in this phrase. But I wanted something short for the very first introduction. I've got some definitions to start with. I define mass as follows. First off, it's measured in kilograms, I should say, abbreviation kg. Note, kilograms is the base unit. Y'all in chemistry class are a lot more common to use grams for your base unit, right? Kilogram is the base unit. If I say that something is 1,000 kilograms, do not type in m equals 1,000,000. If I say that you've got 5 grams of something, do not type in m equals 5. M would be what, 0.005? I'm going to default to giving you kilograms. But every once in a while, there will be something in grams, or you would be using the lab equipment, see something in grams. That's not the SI unit. That's not our base common unit. Anyway, mass is measured in kilograms. I very frequently say kilos. Mass measures the quantity of a substance. It is not the same thing as the weight of the object. There is a big difference there. I will test you on this, either on the midterm or the final. Briefly, mass never changes. Weight, I mean, the Catholics here may be able to attest to this. Hey, mass never. Okay, anyway, mass never changes. Weight depends on whether there's a planet nearby. Weight depends on gravity being around. Weight is the interaction of a planet and you. In deep space, you step on a scale. Well, you can't step anywhere. You're floating in deep space, right? So there's nothing to pull you against the scale. You are weightless in deep space, but you still have mass. If somebody gives you a shove, you don't go shooting off into outer space at 1,000,000,000 miles an hour. You still have inertia. By the way, I define force, the strength of a push. I said somebody gives you a push. How do we measure that? Force measured in newtons, N, is the strength of a push or a pull. How hard you shove somebody. I want you to take somebody and shove it. Shove an object moving along a frictionless plane. Force measures how hard you shoved it. The other word I just used 2 seconds ago, stuff with mass has inertia. Well, what is inertia? The idea of inertia is opposition to changes in velocity. Muy importante. Change. in velocity. If a truck is going at 50 miles an hour and barrels into you, do you notice that it is hard for that truck to suddenly stop? And you're going to die, right? This bowling ball, I've actually got to exert a force to slow it down, to stop it. It has inertia keeping it moving until I stop it. And that doesn't stop instantaneously. The faster I roll it, the bigger the bowling ball. I like big balls, and I cannot lie. The faster it's rolling, the bigger, the more massive it is, the more inertia it has, the more opposition to changing velocity. Also, the more opposition it is to starting motion, right? Yeah. If I've got a heavy bowling ball versus a light marble, heavy bowling ball requires some significant push to get moving. It opposes the change in velocity. It doesn't oppose velocity itself. Example. Shoop. Look, its inertia is keeping it moving along. Inertia doesn't mean that it stops moving, right? So inertia opposes motion's change. Inertia is not the property that things don't like to move. That's not a true statement. Newton's first law. Everything with mass, which is everything that we ever talk about in this class, has inertia. Bang. Newton's first law is not whatever BS was taught to you in grade school. I want you to forget everything you've ever heard about Newton's laws and learn my form. Sure. 2 seconds. Okay. I want to emphasize this. I don't often ask you to be able I like it when you put things in your words. I like to have more than one way to say it, except for this. The grade school version or a high school version of Newton's laws suck. And in my experience, they give rise to a lot of mistakes. I want you to learn my way. Everything with mass has an opposition to change in velocity. Oh, words. Yes, opposition. Opposition means a resistance to, a desire not to, fights against. So inertia is that property of everything that stuff doesn't like to change how it's moving. That's the idea. That's Newton's first law. Stuff tries to keep moving in the same way, same velocity. No. It is a tendency. It doesn't require a force to move. For instance, consider this. When you stop exerting a gas force on your car, you take your foot off the gas pedal, do you instantaneously stop? Does it require a force to keep you moving? No, no. There's drag force on your car. The air is pushing against you. I mean, check that. Stick your hand out the window and you'll feel that air pushing against you. But that is a force of something else slowing you down. That's not intrinsic to the nature of motion. Drag, friction is not intrinsic to motion. Look at the moon. It's been spinning around the Earth for 4 billion years. It requires precisely 0 force to keep it moving at its current speed. As we'll find out, it does have a force on it. That force is very important, but it does not speed up or slow down at all as it's orbiting around. Question? Say that again? Will we be asked what? Pneumatics? What? Numerical, yes. Yes, we'll learn how to calculate these things. Well, inertia, no. Inertia is a principle, an idea. Things resist change in velocity. That doesn't have a calculation associated with it. Second law does. So I guess, no. Inertia, no calculation. Okay. Example, car on the highway doesn't just instantaneously stop when you release the gas pedal. The slowing down of the car comes from something pushing on it. The air pushing it, slowing it down. This bowling ball, for it to move along does not require that I keep kicking it, right? If I keep kicking it, ow, freaking stubbed my toe. If I keep kicking it, it's sped up as it went along. That's Newton's second law, incidentally. Okay, so If something is moving, it doesn't like to change motion. It doesn't require a force to keep going. It doesn't require a force to have a velocity. It requires a force to change that velocity. Turn to your neighbor and express this idea real fast. Okay, let's bring it together. If I have a steady force on an object, I do not get constant velocity. For instance, the force that we've talked about so far that is constant, that doesn't depend on where you are really, it doesn't depend on which direction you're moving, is gravity. Oh, look, it was moving slowly at first, see, barely moving at first, and then when it hits the ground, it's moving quite quickly. Its velocity accelerated. Force is not required to have a steady velocity. Force is required to change that velocity. Force is an interaction. For instance, to stop its downward motion, the ground had to touch it. It had to touch the ground. Then you change the velocity. Without the ground, it would have continued moving. Follow-ups. Question me.
Like I understand like the concept of you added force onto the bowling ball. You don't need to constantly continue adding force in order to move. It's able just to move on its own. I'm still kind of confused on like how that correlates with the definition of a position that changes. Like
So the law, Newton's third law, is stuff has inertia. Inertia is the resistance to change. I mean, ASU, metaphorically, has got a lot of resistance to change. It's got institutional inertia. To keep going as it is doesn't require effort. You want to change the way we do business here? Now that's hard. That makes people angry. Yeah? So inertia is the fact that it likes things like to stay as they are, and in particular, that velocity likes to stay what it is. The first law is to say that everything has that property. Some more, some less. If I have a car going at 5 miles an hour and I stand in place, it may very well break my legs. If I have my son running at 5 miles an hour into me, I just catch him, pick him up, whee. If I have this bowling ball going at 5 miles an hour, oh, that, ow, well, no, it's okay. That didn't really hurt. I was just pretending for reals. You know, it barely does anything. A mosquito flies into me at 5 miles an hour. I don't even notice it until it stings me, bites me, right? So different things might have different amounts of opposition to changes in motion. What we will discover, the difference between these is, what do you think? Mass. Mass never changes for a given object, but mass causes more or less inertia for a given amount of velocity, bigger mass, bigger oomph. Okay. So Newton's first law tells us that stuff doesn't like to change its velocity. Newton's second law tells us, well, what does change velocity? What does accelerate an object? To change an object's velocity, to cause an acceleration, thou shalt apply an unbalanced, a net force. Net has nothing to do with fishermen. For physicists, net means total. Add them up. Add up the different forces acting on it. There must be not canceling forces. I want to emphasize unbalanced net or net force does not mean just that there's only one force. This bowling ball has a weight force on it now of something like 50 newtons, I think. Does it accelerate? Look at it. Is this sucker accelerating? No. Negative 50 newtons of weight force does not cause it to accelerate. Why? What's balancing that? From what? What's causing the upward force? The floor. The floor is exerting a support force, what I'll define later as normal force. You can write that down there. So there's a negative 50-ish newtons downward from the ball. There's a positive 50-ish newtons upward by the floor. The total of plus 50 and minus 50 is, last I checked, 0. What happens if I accelerate this upward? I'm going to accelerate this upward. What happens? Were the forces balanced? No. To accelerate something, I've got to push it with a force harder than Earth is pulling it down. If I continue to push it with an equal force to the planet, nothing's going to happen. What about to have it move at a steady velocity? Does that require that I exert a big force? No. If I move this up, move this down, oh, I'm getting exercise. But moving it up and down at a steady rate, I don't need to apply more force or less force than gravity. Moving at steady velocity is not an acceleration. So if I move this at a steady rate, if I put this in an elevator going at a steady rate burns no fuel to the extent that or uses no electricity except for, just countering friction. We'll do more about this. We'll give more examples of this in a second. Here's how to calculate the magnitude of the acceleration. The acceleration of an object, the change in motion per second, is equal to the total force, pluses and minuses, added together, divided by the object's mass. This is the most common equation used in this course. You will use it approximately 1 billion times, more or less. Total force. Total force. You cannot just use, there's a 50 Newton weight force on this bowling ball. I cannot plug 50 into here. If I plug 50 into here, the guy's mass is like 5 kilos, I think. If I plug 50 into here, I would conclude that it is accelerating. That's not accelerating, it's just sitting there. Right? Okay, how could I find, when would I plug in 50 newtons here? Now. If I only apply a weight force, if I take my hands and the table away, the only force is the weight force, then it is, you betcha, gonna believe it. But you better believe it, it's going to accelerate because there's an unbalanced force. There's nothing supporting it. There's no positive force on it. If I move downward and I'm slowing down, point for me, which direction am I accelerating? Move downward velocity, negative velocities, and slowing down. How do I slow a negative velocity? Which direction do I point? One point. Let me see. If I'm moving negative and slowing, I better be adding positive numbers to get those negatives closer to 0. Positive acceleration is the correct answer. There's a test question. Merry Christmas. I mean, like we've been doing this for a couple weeks now. Moving downwards and slowing downwards is a positive acceleration. Riddle me this, Batman. An elevator which is going down and slowing down, which force is bigger on someone standing in it? I'm standing in the elevator, I'm going down and I'm slowing down. Is the force of the floor supporting me bigger, the upward force, or is the weight force pulling me down bigger? Don't you feel compressed? You feel pancaked, right? You feel like you're heavier. You're not actually heavier. The floor is pushing into your feet more to slow you down. Weight doesn't change when you're in the elevator. Gravity doesn't change, right? The earth doesn't care that you're in an elevator. The earth is going to pull down on you with a steady 500 odd Newton force. What is happening to slow you down, to accelerate you upward, to have a total positive force to give you a positive acceleration is the floor pushes you harder than the earth pulls you down. Moving downward and slowing down, positive acceleration. The total force must also be positive. Mass is always positive. No one's ever observed negative mass, even in advanced physics. So the direction of the force and the direction of the acceleration are always the same. If acceleration is positive, total force must be positive. So your upward forces, your positive forces, the floor pushing you up must be bigger than the weight force pulling you down. Turn to your neighbor and discuss. This wrecked my 3 o'clock. They died. There are multiple ideas in here. Where's it go? Because velocity doesn't show you, velocity shows you the direction of motion. And if I go from a negative velocity to a 0 velocity, the increase, that's an increase along the number line. Acceleration is positive if I go from negative to 0. That's a huge thing. That will be at least 2 questions on the midterm. Questions that go back to that. Negative number to a smaller negative is an up. Hey, real quick, quiz question. Let me give me a point up or point down. I'm going to have a positive acceleration. Something is accelerating upward. Which direction is it moving? Point. That's correct. We don't know. Tell me why. Tell me why. You get an A. You all get A's. If you're in them. Okay, someone who said we don't know, tell me why. That's exactly right. Direction of velocity is independent from the way that velocity changes. Velocity's sign shows you the direction of motion. Acceleration sign does not. Acceleration tells you how v is changing, not what v is. Okay. Moving downward and slowing down means upward acceleration. You have to add to a negative to get closer to 0. That's hard. We've been doing it for a couple weeks, so I'm hoping that it's making less nonsense. I'm not claiming that it makes perfect sense, but hopefully it should be less hard. Give me some feedback. How do you feel about this? Solid. Great. Want to ask a question? No questions. Really? Please. Can anyone propose? Think about an elevator. When might the total force on an object in an elevator be downward? When you're speeding up while moving downward. For instance, I get into the elevator on the 3rd floor, punch 1. Don't you feel less compressed? Don't you feel your stomach lift? Well, actually, that's not quite what's happening, but don't you feel less force on your feet when you are accelerating downward? Weight doesn't change. Weight is not changing. The earth doesn't care that you're moving downward, accelerating downward, whatever. The floor is not pushing up on you as much. The floor is moving down around you. That's what happens in an accelerating downward elevator. Here's another example of when you might accelerate downward. You're moving downward and speeding up, or you're moving upward and slowing down. Don't you feel whoa when you get to the top of the elevator ride? Right? When it's stopping at the top of the elevator ride, the elevator isn't pushing you up as much as the planet is pulling you down. You are slowing your upward motion. You are slowing your upward motion because I've got a negative net force on you. I'm subtracting off of your upward motion. I'm subtracting off of your upward velocity with a negative acceleration. We're going to do like 80 billion examples of this. If this doesn't make perfect sense the first time, you're okay. Keep going. I want to emphasize something else. We talked about the direction of acceleration and mass being the same. Let's talk direction of acceleration and the direction of force being the same. Mass doesn't have a direction. Let's talk about the mass part. What mass the divided by m reflects in here is if I kick a ball, its velocity changes. Now I kick a bigger ball, kick a boulder, I would have to kick a lot harder to get a bigger ball moving in the same way, right? Flick a marble, goes flying. You gotta kick a bowling ball to get it go flying. Ow, right? So if I have a bigger m, the same force gets a smaller a. Downstairs of a fraction goes up, the answer goes down, right? Turn to your neighbor and express this point real fast.
I don't know how big this crowd is, but it's going to need a lot of noise, okay? Hang on. Your mouth. You're going to practice with that same face. Yeah, see, I like the facing. There you go.
No, for a bigger ball to speed up is because it has more inertia.
And ultimately, mass is how we measure inertia. One way to measure inertia. Yeah. Good. Okay. Questions? Please. I mean, think about it. What if the elevator went away completely? Ooh, but I mean, wouldn't you continue to move upward? Your inertia carries you upward, but you'd slow down. That's just like here's something moving upward and slowing down. Yeah, as it was rising up, there was a net negative force on it, slowing it down as it rose. Okay. Next slide, please. Newton's third law is way harder than Newton's first and second put together. In my experience, based on number of mistakes made on tests, homeworks, whatever, Newton's third law is hard, but it's okay. We're harder. Grr. Okay, so I'm going to give you a lead up to Newton's third law instead of just stating it. First off, can I fly by pulling on my bootstraps? Let me test that. No. Can I get a big freaking fan on the back of a sailboat and get it to zoom out of there? There's a recoil for the fan. Huh? The fan has a recoil. It blows the sail, but the air it's pushing recoils the opposite direction. The boat don't go nowhere. Um, can I push myself? Can I get myself moving that way just by pushing my side? Okay, I'm not very strong. Try it yourselves. Can you get yourselves moving by pushing on your side? No. Point one to understand the third law is you cannot exert a net force on yourself. That's not to say you can't push parts of yourself against parts of yourself. I'm pushing my left hand on my right hand. That's a very real force that my left hand is exerting on my right hand, but nothing that I do is going to move my total body. Nothing that I do pushing body part on body part is going to accelerate my body away. That was fun. Did I run by exerting a force on my legs? No. Did gravity point sideways for a second? I will tell you, except for gravity, everything we will do this entire semester requires touch. What was I touching? The ground. Ultimately, why you walk, how you drive a car, how you brake, how you stop, it is the ground pushing on you. It is very important, not when you don't want to, in order to avoid screwing up Newton's third law, you must identify the objects which are interacting. Every force is actually a pair of forces. Every force is an interaction between exactly dos objects. Two, if you don't speak Spanish. I want to emphasize what's an object, because this gets some goofs as well. To be an object, it must be possible in principle to lick it. I have students tell me that the reason objects fall, the object which is causing the interaction, what object is exerting a force on this pen, they say is gravity. You cannot lick gravity. Gravity is an idea. Gravity is the title of a chapter. Gravity is not a thing. What object is accelerating my pen downward? Turn to each other and discuss real fast. What object is causing it to fall? It's not me. Is the air pushing down? I'll give you a hint. If you go far, far away from this object, there ain't going to be no fall. The correct answer is the planet. If you take the planet away, go into deep space, the pen's not going to accelerate. Okay? Just let it float. It will just float. Again, if you said the thing, the object that causes it to accelerate is gravity, then go to jail, go directly to jail, do not pass go, and do not collect $200. Okay? Gravity is not a thing that can be licked. The planet is a thing that can be licked. Another example, if I kick a ball, the interacting objects are the ball and me. The kick is not an object. The kick is the force.
For the third law, can we pass a statement like every object has an equal and opposite reaction?
No! I want you to forget that. That doesn't exist. We're not there yet to the third law, but I want you to forget that that sentence even exists in the universe. That leads to so many mistakes. It is such a seductive misinterpretation. There is such a seductive misinterpretation. Please forget that it exists. I haven't defined it yet. This is a lead up. Okay, so again, to understand the third law, thou shalt understand that forces reflect interactions between exactly two objects, and to avoid screwing up, if you want to escape failing this law, you have to recognize what objects they are. Another example, a boat is sailing on the ocean. Oh wait, Arizonans, do you guys know what the ocean is? Big bathtub, there we go. Okay, so discuss with your classmate what two objects are involved in floating. You must be able, in principle, to lick it. In principle, it must be lickable. If you said buoyancy, go to jail, directly to jail, do not pass go, do not collect $200. Buoyancy is a subject title. It is an idea. The water is a thing which could be licked. Water is the correct answer. Boat and water. I'm a jump. I claim that I have a force that the earth exerts on me. I call that force weight. I ask you this, as I fall down when I am in mid-fall, does the earth feel pulled up? Talk to your neighbor. Does the earth get pulled up as I fall down? Do I gravitate the earth? Discuss with each other. Argue about it. Believe it or not, the earth does feel a force. And it's in fact exactly equal to my weight force. However, my weight divided by an literally astronomically large mass means that you're not going to observe the acceleration of the earth falling up to meet me. In principle, though, it's there. There is always a force pulling back. It's not just on yo mama that gravitates. Yo mama is so gravitational. The thing is, I'll give you a pre-explanation that we won't do for a while. Gravitational force depends on the product of the two masses. You want to observe it? At least one of those masses had better be big. Okay? So the Earth and me, the Earth exerts a force on me, I exert a force on the Earth, same magnitude of weight force, same gravitational pull, because the Earth is really honking big, even if I'm small. You are not attracted to your classmates, at least gravitationally, because both of you are not astronomically big. What? It depends, the actual weight force depends on the product of the two masses. To exert a significant force, measurable force, at least one of those two things multiplying has to be astronomical. Question?
Two objects have exert a gravitational force on each other.
Mm-hmm. Always. Any two objects. To speed it up or slow it down, as it turns out, there is a weight force. The Earth does pull on the moon and the moon pulls on the Earth. You could tell the moon pulls on the Earth. Why? The tides. The tides are a lunar effect. Okay, so. That is a turning force. The direction of motion is this way of the moon. The direction of force is this way. That does not speed it up. That does not slow it down. That turns it. We'll get there later. Okay, so remember this. We're going to talk about this. This is a test question. If you pull the Earth pulls you. If the Earth pulls you, you pull the Earth. And that's the third law. I've said it 3 different ways here. And then there's an important point about the nature of those. Every force is a pair of forces. Every force acts on 2 things. Every time 2 objects interact, each object feels that interaction. A third way of putting it, The interaction, the forces felt by each object are actually, it's the same force. It's just felt from a different perspective. You want equations, you want to plug in numbers. The numbers, the strength, the magnitude of the force are equal. Is the effect, is the acceleration equal? Not necessarily. But the amount of force is equal. The direction that those forces exert are opposite. The magnitudes are equal. Example, you could test yourself. Both of my hands feel a clap. Try it yourself. Clap your hands. If one of your hands feels different than the other hand, go to a neurologist, please. Because I promise physics says those forces are equal. Clap your hands softly. Clap your hands really hard. Yeah? It's impossible to exert a different force on your left than your right hand. It is impossible for the force to be different. It is absolutely impossible to clap one hand on the other harder than the other claps back on the one. That doesn't mean the effect has to bring equal motion to rest. For instance, I'm going to clap this hand that's supported by the table. This hand accelerated, it stopped moving, right? It was moving down, then it stopped. They both felt the, they both felt the clap. Try it yourself. Put one hand on your lap, clap. They still both feel the force. Now clap something bigger. Oh, well, maybe not. Both my cheek and my hand felt the force. Yeah. The force is equal in either case. 20 minutes. I want to do more examples. I want to do more examples with this because it is so very easy to screw this sucker up. Can you kick this bowling ball and accelerate it, get it to change its motion without stubbing your toe at all? I'm assuming you don't have steel-toed shoes. It's impossible to accelerate something, to change its motion, or for that matter, to stop it. You know, you throw this at my face, I'm not gonna be able to stop it without hurting. I can't exert a force on this without it exerting a force on me. Moreover, it's an equal force, equal magnitude, although if I push this backwards, my nose pushes this, stopping its this direction motion. Stopping this direction motion is a force that way. It pushes my head backwards that way, opposite direction. Who shot a gun before? Did it kick? Did it kick hard? Yeah, it's impossible. Physics says it is impossible to design a gun with exactly zero recoil. Every gun has some recoil. And if you get a gun with low recoil, there's fancy engineering that had to be done to absorb some of the recoil. It is impossible to have a zero recoil gun. Anytime you get bullet to go this way, the gun goes that way. Okay? Think about it. Does the bullet go faster or does the gun? Hopefully the bullet's going faster. Bullet's going this way at like 100 miles an hour. The gun recoils at hopefully a couple miles an hour, an ow mile an hour, pushing into your shoulder with a rifle, whatever. Okay. The gun is bigger. And you are exerting, hopefully, a force on the gun as well. I'm not claiming that if you propel something 100 miles an hour, you have to recoil at 100 miles an hour. Depends on your mass, depends on other things interacting with it, right? Nevertheless, the forces are equal. The bullet pushes backwards on the gun. Question? Say that again? If you kick a car. Oh no, the car has to recoil a smidgen.
It doesn't.
There might be other forces acting on the car, a bigger friction force, whereas the ball goes whee. It's a smaller mass. Newton's second law guarantees the acceleration is bigger, and I don't think that the friction on like a beach ball or whatever is going to be significant compared to your kick. So 2 reasons really. Good. Yes, though, yes. Question?
For analysis purposes, forces we're gonna, are we to ignore friction and other forces and acting for like practice problems in the exam?
It depends on the problem. If I talk about a parachutist, if I talk about a piece of paper or a feather drifting, air is important. If I talk about someone skidding to a halt, a car braking, friction's important. Most of the time, though, I will be focusing on when we've got a simple scenario, and I will try to reduce the number of forces under consideration. And I word it as often as I can, as precisely as I can. I will talk about on a frictionless surface, on a smooth track, a car drives onto ice or whatever. Those are hints that I'm saying, ignore friction, let's just focus on the other things. Hey, what happens if you're on a really icy surface? Can you turn? Anyone grow up where there's ice on the road? Can you turn when you're skidding along on the ice? You cannot change your velocity. Can you speed up? Can you brake on black ice? No way. Your velocity does not change, Newton's first law, because the ice does not exert a friction force on you. But likewise, what happens if you start on that ice? Can you move anywhere? The ground does not exert a friction force on you, moving you. Question?
And as you said that the forces are equal, which is the recoil and so the net force is zero.
No. Two different objects. There are two objects with two masses. The net force on the bullet is very much not zero. There's only one thing pushing it. We would ignore drag in this circumstance. There's only the explosion of the gunpowder pushing it forward. The net force on the bullet is not zero. The force on the gun is not zero.
So when you said that the forces are equal,
Yes, the force is on different objects. That's true.
fixed,
Yes,
the acceleration would be different.
the acceleration has to be different if the same force acts on different masses. Yes. I want to emphasize something here. Another very common goof is to say if forces are equal, then they balance, then there's no acceleration. No! Those forces act on different objects. The Newton's third law of forces act on different objects, never the same object. That's why I want you to go to significant effort to identify what two objects are interacting. They are different objects. They feel the same force, but you cannot add the forces on two different objects. Net force is on one object, causes one object's mass to experience one object's acceleration. You want to understand the acceleration of two objects, you have two equations. We'll get there. We're going to do a bunch of practice with one object first, then we'll talk about multiple objects at the same time. I'm going to give you a couple of forces to be able to start with. A couple of forces to start with. First off, I define weight is the force of gravity, the force that a planet or star or a moon exerts on something near it. Weight is not the amount of stuff. Weight is how hard it's pulled. What's the unit of force? Newtons. What's the unit of weight? No, I just said weight is a force. No, I just said weight is a force. You said the force is measured in newtons. Weight is measured in newtons. Kilograms are not a force. Kilograms are a mass. Now, you will see conversions on a scale. You can get the number of grams in a substance that assumes you're on Earth. If you go into outer space and you put your 5 grams of carbon near the scale, it's not going to read. Scales don't measure weight. Scales measure the force they're pushing against. Question? That's true? Oh, they relate. Absolutely, but they are different things. A kilogram measures how much of something. A Newton measures how hard it's pulled. And we only can have conversions between those things when we have, an established we're applying in the same gravitational field. For this gravitational field, I could say that 1 kilogram weighs 2.2 pounds. But I'm comparing two different kinds of things. Pounds, by the way, pounds are not mass. Pounds are force. Conversion factors between pounds and kilograms are actually physics nonsense unless you specify on Earth. If I go onto the moon, a scale measuring kilograms is going to give you the wrong answer. A scale that is calibrated to kilograms is going to give you the wrong answer. It will, however, if you talk about the newtons exerted on the moon, that weight force would read correctly. Okay, so again, mass measured in kilograms, weight measured in, force measured in newtons. Weight is a force. Good. Okay, let's find the force equation. The force of gravity, the weight force equation. I'm going to symbolize all the different forces, well, most of the different forces with different letters because I don't want you to get Fnet and F1 and F5 and Fs get confused with each other. They all look like F. I'm going to put different letters very commonly on the different forces. Different force types. There are lots of types. And they're all pushes and pulls. They're all measured in newtons, but they have distinct characteristics for each sort. Weight force goes by the equation negative mass times what's G? Nope. Gravitational field. Gravitational field. Don't say gravity. Gravity is a chapter title. It is neither a lickable thing, nor is it the name of G. This is gravitational field. It's also not the acceleration of free fall. Okay, let's plug in what happens if we apply the weight force and say that something does, only force is the weight force. What happens if you shove negative mg into Newton's second law?
Why did you say G is not the acceleration?
G is only the acceleration of an object if it is in free fall. Right now, G is still applying a weight force to this object, and it is not accelerating at all. 9.8 newtons for each kilogram. This is not accelerating at 9.8 meters per second squared. Look, it's just sitting there. Nevertheless, there are 9.8 newtons for each kilogram of mass. G is 9.81 meters per second squared or newtons per kilogram, which are the same units, just different forms. But I don't want you to think of this as an acceleration. I want you to think of this as how hard each kilo is pulled if you drop an object, if the only force is weight. What happens if I shove negative mg in here? If the only force is weight, I shove mg in there, mg over m cancels, and a equals negative g. Sure, if you drop an object, if the only significant force on it is gravity, is weight, then it accelerates downwards with a magnitude equal to the gravitational field. But they're different. This equation is two different kinds of things. Here is a cause, and here is its effect. Gravitational field tells you how hard 1 kilogram gets pulled. You drop that object, that value is also how much it accelerates, but G is still applying to this object at rest. G is always applying anyway, anytime you're near the surface of the Earth. A might be any different number depending on the situation. Remember that exercise that I gave? Is it possible for a car to accelerate at G? I mean, that depends on the car, but yes, it is possible for an object to accelerate at 10 meters per second squared. Yeah? Did I say that in class or was that in lab only? Does a car always accelerate at G? No, my car most definitely does not accelerate at 10 meters per second per second. Okay, I got a junkmobile. The dealio, Julio, is that 9.8, you can plug in 9.8 meters per second squared downward if and only if you are in free fall, if it makes sense to plug in A as negative G. Okay. Big deal, big takeaway from this slide, big deal. Big takeaway here is that I'm giving you a weight force formula. Weight equals negative mass times field. Now I'm going to tell you one other thing, and that is the formula for normal force. Before I tell you this, N, normal force, there are a couple warnings. One is the symbol I use for this N is the same as the symbol we use for newtons. I'm sorry, it sucks, but we ran out of letters. So, normal force equals blah, 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 blah. N equals blah, 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 blah. I'm talking about the normal force. Some number with an N after it, that N is talking about the unit newtons. You see the distinction? If I say something equals 5G, what am I saying? That thing is 5 grams. If I say G equals, better be 9.8 meters per second squared, G equals 9.8. So G can either be the variable or a measurement. Normal force, N, is different from the measure of it, the unit of it, the Newton. Watch out for that. Pick it up from context. Okay, so normal force, ow, is what just hurt my hand. Normal force is what solid objects exert on other solid objects. Okay, this table is exerting a normal force on this bowling ball. Actually, the table was still exerting a normal force on the bowling ball, and that's what caused the bowling ball to roll downhill, ultimately. More on that in your lab. The support force, the normal force, also has nothing to do with usual force. Oh, believe me, it is very common to have a normal force, but normal does not mean usual, and normal is most certainly not in every problem. Look, just drop something. There's no normal force right now. Now there is. Now there is. Not now. Whoops. When something is falling, there's no surface exerting a normal force on it. Okay, so weight force, negative mg. Normal force, psych, we should be so lucky. Don't go away. I have a point to make about this. You will calculate normal forces, but you will not calculate it with the same equation every time. You will deduce normal force based on other things you know. For instance, that 50 Newton ball is not accelerating. What's the normal force on it? I would say positive 50. The table is opposing the negative 50 weight force. Weight force goes down. So I'd say, you could say the magnitude is 50, or you could say the force is positive 50 newtons. How did I get that? Is there an equation that says normal equals 50? No. There's an equation that says net force is 0 if he no accelerati. The only way to balance out a downward 50 newtons is with an upward 50 newtons. Do you see? We're not getting normal from an equation. We're getting a normal from an idea. We're out of time. If you have further questions, come on up. Otherwise, you are free.